All right, so what we are looking at in this video is something that's known as a back-propagation algorithm, the famous dynamic programming algorithm, and it allows us to get the gradient of the error that we were interested in an efficient way. And we'll after that, we will use gradient descent algorithm to fit the data. So that's the goal for this video. And to implement gradient descent, we need to compute the derivative of the error, right? And so that's what we will be doing in the back propagation algorithm. And what exactly are we after is, as I said, the derivative of error with respect to the weights for, let's say, layer L. So we will derive back propagation, again, as I said, which is a dynamic programming algorithm that will compute all these gradients in an efficient way. So what do we have to do, right? We have this matrix here. We know that this WL is a matrix of weights, right? And we are supposed to compute the derivative of the error with respect to that matrix, which in itself is quite a difficult task. And let me quickly give you an overview of what exactly we're supposed to do. So let us assume and what's happening essentially and how things will play in this. So let's say this is some layer, let's say L, right? And there is this input that's coming into my layer L. And if you remember, the way we denoted the input is like S of L, right? And there is some node, let's say I, in this layer. And once the input comes in, the transformation is applied, theta. And then I get some output, which goes into another layer, which I'm denoting by X of L. That's another layer. And what's happening when we are coming in here? So there is, as I said, this matrix of weights, remember? And that's what we are denoting. That's what we are using this WL for. And what it comprises of is, let's say there was another layer, and of course there is, if at least there would be an input layer, and that gives in some X, let's say XL minus 1, of course. And using that, now I'll have for some node I, I'll have let's say WLI, right? And each of these WLIs will be vectors, column vectors in this matrix. That's the idea. So, as I said, WLI is a column in this weight matrix. And remember, the error has to be, the derivative of the error has to be computed for the entire matrix. So let's see how we do that. Getting the derivative of the error with respect to, so we'll begin with this. I'll get the derivative of the error with respect to Wi of L. And then we'll expand that. And what exactly is this term doing, if you think about it? Now this is impacting the signal going in node I, right? And so of course it's in some ways impacting the signal that's going in, and it's the weights are affecting that. So I can break it down. I can break this down using something that's known as chain rule, and you must have come across in your one of the classes where you did the derivative and then other calculus stuff. So using that chain rule, I can break it down to make it more convenient, in the sense that I can make it such that it is the component of this is a signal change and the error change with respect to the signal. Well, let me do that on the next slide. So again, I'm rewriting it. I'm interested in just this column I, which can be written as delta, and then this is SI. S, remember, is the signal for linear, for layer L. And yes, we said this is a linear signal. So that's this, right? Multiplied by the change in error with respect to this input signal. And we'll see why we are breaking it down in such a way. We're breaking it down in such a way because we know that, I know that this SI, this linear signal for node I in layer L is, and we got that in the some time ago, right, is nothing but W transpose X L minus 1, because it's the signal, the input that's coming from the previous layer times the weights that I just whatever the weights here are, right? That's what's making my linear signal. And so because I know that, then obviously I know, and then let me like make a small box here for this one separate. I can calculate this delta Si for layer L with respect to the weights, right? And that's what this term is, right? So if I go and like find the derivative of this WIL, you can tell just by looking at the expression on the right hand side, this derivative will just be the coefficients, right? And so my coefficient is nothing but my XL minus 1, right? So therefore, my delta E weights L will equal, this term is just the coefficients from the previous layer, right? The actual input, and then delta E, and this term stays the same. All right, for I layer L. Okay, so we started by saying that I'm interested in the derivative of the error with respect to the entire weight matrix. I have it for a column, and so I can translate this to the entire matrix, which is nothing but something like this, WL, right? And this is going to be the derivative of the error. So that's going to be a vector of derivatives, right? Derivative of the error with respect to the first signal, derivative of the error with respect to the second signal, and so on. And so this, like this column, this result for only that one column will then translate to the entire vector, which I'm going to write again and then rewrite it. XL minus 1 will stay, and then delta E, delta S1 and L, and then XL minus 1, delta E, delta S2, L, and so on, like depending on, let's say there were D such nodes, and so I'll have like delta E, delta S, L, D of L. All right. So because this is like the vector of derivatives, I can write in like a more compact form because XL minus 1 is common in all of them. And this here is going to be nothing but delta E, and we have the notation for the entire, like the components for S, and that is going to be SL, right? Transpose. Okay, so this term here is nothing but the vector of derivatives. All right, and this here is the output of the previous layer, right? Previous layer. Right, so let's use this term, which is like the vector of derivatives, and like define it in like a more generic way. I'm trying to like come up with a more generic definition for this particular term, and that is known as the sensitivity. This is the sensitivity of my error with respect to the input to my layer L, right? And sensitivity can be like defined if we have the input. For example, if we make some change in my weights, then the inputs are going to change. And that is somehow captured by this sensitivity or by this term. And the way we denote it is known as like this is just like I'm writing it here. This is a delta. And this is how we are going to denote this sensitivity. So this term is essentially representing the sensitivity in a certain way. So my delta E or delta W for layer L is the input, the output from the previous layer times the sensitivity for that layer. All right. So now the question arises, of course, all of this is fine. I have like this expression for my derivative of error with respect to the weights, but what exactly have I gained? Because all this is done for like some kind of computation, but we still want to compute the derivative of the error with respect to my signal because that's what my sensitivity is, right? And so let's see if we can do something about it. And let me like quickly try to kind of check the components of like this sensitivity itself. And so this is for the entire input signal, and this has like components for every node, right? So therefore, like let me write it separately. Component wise, if you're looking at it, I have delta Si for layer L, right? And then again by chain rule, I can break it down in terms of the output from this layer, and I can say that this can be rewritten as delta XIL times delta XIL delta SIL, right? This one component, and although this will have like, this is the entire vector, of course. But also, why we are trying to break this down? We are trying to break this down because I know something about my x of I, and I know my about my x of I in terms of my input s of I. What exactly is that? Well, remember the activation function, the theta that we chose. And so xi of L is nothing but like some calculated value that's coming from my input signal, right? So this is nothing but theta of Si of L. And yeah, that's it, right? If it's like, if I apply this theta on this S, then I get my output, that X, right? And so how does that impact like this equation? Well, it does, because now I'm finding the derivative of, like, if I replace this xi of L with this theta, essentially I'm saying the derivative of theta evaluated at Si of L, right? So therefore, I can write this delta E delta Si of L equals the derivative, and this like small, I don't know, this prime thing is saying the first derivative, right? Evaluated as at SIL, right? So that's this term here. And then I have like the first term, of course, stays, which is the derivative of the error with respect to my x of L. All right. So this is like one of the component for my error, which was this thing, right? And of course, like this will have a vector of derivatives. So we need to like collect all the components and write it in like a more concise form. And the way we write that is that we'll use some other notation and like just expand this, I would say, over the entire like vector of components. So here it's going to be the derivative computed at S of L for each one of those, right? Each one of the nodes essentially. And then I'm using this notation. This is sometimes also known as like O times, because like we are doing component wise multiplication, right? Because both of them are like vectors. So let me do the component wise multiplication. I'll do delta E over delta XL, right? And XL from component number 1 up to D of L. It was D of L, right? That's what we started with, so that's fine. Now here, what are we saying like in this like math equation? So essentially we are saying the sensitivity of the error with respect to the input in my layer L, which is this, right, equals the derivative of the transformed function evaluated at the input, right? And then that's like multiplied by the vector of derivative of error with respect to the output for this layer. Okay, so all of that is great, and we are still not done because we need a more like a better way of like doing something about this like second term, which is like this vector of derivative of error. And let's see if we can evaluate this term with the chain rule and make it like even more simpler. So that's exactly what we're going to do, and let me just like begin here and then we'll move to the next slide. So exactly what I'm trying to do is I'm trying to calculate this thing, right? And again, using the chain rule, this is also like all this applies to all the nodes, right? And so I can write it as a summation of all the nodes starting from 1 up to DL plus 1. And that is because I'm this L, this is the output from L to L plus 1, right? My XL is the output to the next layer, right? So that's what I'm going to do. I'm going to break it down. This is nothing but the sum of K equals 1 up to DL plus 1. This is, by the way, plus 1. And delta E, so we have to compute it for like all the components. So delta SK L plus 1. This is delta. That's making some weird. And this is delta SK for any kth node, L plus 1, and then derivative with respect to x of L. Okay, now why am I trying to bring everything to this S value? Because the thing is that I know the definition of this like input signal. So basically, since, and I'm using this symbol for since, SKL plus 1 is nothing but this W K by definition, L plus 1 transpose and XL, right? I know this. And what I can do is I can substitute, like using this expression, I can evaluate the second one, which is like delta SKL plus 1, the derivative of SKL plus 1 with respect to XL. I can do that here, right? And so what I'm going to get here is that this is going to be WL plus 1K. That's it, right? And so I can replace this term here, right, by, so therefore, let me write it, therefore delta E delta XL, right, equals the summation from K equals 1 D L plus 1, and then I have the derivative of that, which is W. So you can calculate the derivative of this, right? Derivative of this with respect to this XL, which is like the second term here, right, is W L plus 1 transpose. That's all that is. So all I'm left with here is this with respect to K times delta E delta S L plus 1. Okay, so why? So if you think about it, this is like the weighted sum of these columns, right? And why is this important? This is important that because like eventually, let me write it down. Like what have I come up with by doing all of this? Well, I've come up with this equation, and now I think you can actually see what's going on. So I have like this delta E delta XL XL is equal to WL plus 1 times the sensitivity L plus 1. Okay, so all of that is great. If you can see that this is nothing but the sensitivity of the next layer, right? So this is my sensitivity for the layer L plus 1. So what happens to our original equation of delta E, the sensitivity of the error with respect to the input layer? Now we have the result for this thing, right? And we already have this. So what does this like equation become? Let me write it down now. So my final equation is delta E derivative with respect to SL equals theta. Now this was the derivative of the transformed function evaluated at the input. We know that SL component-wise multiplication with nothing but WL plus 1, which we just got from here, right, times delta L plus 1. All right, and then this is like component-wise multiplication up to all the components. Okay, so what have we achieved after doing all this algebra, all this like derivation, and like eventually getting at this particular equation? What have we achieved? Now, if you look closely at this equation, right, you are trying to compute. Now, what is this on the left hand side? Delta E delta SL. Let me take you back to one of the slides where we defined something that was known as sensitivity, right? Sensitivity for certain layer, which was like how much my error changes with respect to the input signal. And this is what it is, right? So this is my sensitivity for layer L, isn't it? And so that's like delta L on the left. But on the right hand side, you can see that there is the sensitivity for layer L plus 1, right? So if you think about it, we have established a relationship. We have established a relation between sensitivities from one layer to another, between sensitivities across layers. Okay, so why is that important? Well, it is important because we can extend this logic, and if we extend this logic in like layer L plus 1, then that means the sensitivity of layer L plus 1, right, is related to the sensitivity of layer L plus 2, and L plus 2 is related to L plus 3, and so on until like the sensitivity of layer L, right? And so the thing that comes to our mind is that if we can somehow compute this, the sensitivity for the last layer, that's like layer L, then I can get the sensitivity of L minus 1 and then L minus 2 and so on until I get the sensitivity for layer 1. And why do we care about it? Well, we care about it because the sensitivity of layer L multiplied by the output of layer L minus 1 give me the matrix of the derivatives of the weights with respect to my, essentially gives me that matrix of the derivatives with respect to WL. And that's what I'm interested in, right? So I know that's a lot of information that's like really, really overwhelming. Let's see what exactly do we need. Let's like summarize and let's write down the most fundamental equations here and then try to extract like what exactly we need for our backpropagation algorithm. Or like what exactly is the backpropagation algorithm. Let's put things in perspective. So we have come up with two things, right? So the first thing that we've come up with is this. So WL equals XL minus 1 times delta L transpose. Okay, what is this? Well, this, and by the way, just like always, remember this, the dimension of this is going to be 1 plus dl minus 1 times dl. You can go and verify this, right? So this is the left hand side. On the right hand side, this is the output from layer L minus 1 times the sensitivity of layer L. Well, we know that we cannot compute this exactly, but we'll see what we can do about it, right? So let's assume this is equation number 1. I'm just summarizing, and this is equation number 2, which is the sensitivity relationship. Now, the sensitivity relationship that we have or we arrived at earlier is that this is the derivative, the first derivative calculated at theta. Sorry, this has to be S and not delta. So let me just erase it. And okay, so this is going to be S L component-wise multiplication with the weights L plus 1 times delta L plus 1. And remember, this doesn't include the bias here because sensitivity we are computing for like from 1 to D, whatever the number of nodes. Now, these two equations are the two most fundamental equations that you need to know in order to implement this neural network that we're talking about. And I'm going to talk about like step by step of how we actually implement that and how we use stochastic gradient descent. Specifically, we're talking about stochastic gradient descent, but the rules apply to the general gradient descent implementation as well. One thing to remember again is that if you focus on this equation, you can see that there is like some kind of a recursion that's happening, right? With every, with some sensitivity information about one layer that kind of propagates to the next layer, right? So we will be exploiting that when we use gradient descent, and that's what we're going to see. So this all has summarized what like the fundamental idea of backpropagation is, but now we're going to implement it so you'll know how this backpropagation takes place. All right, so as I said, we will talk about something that's known as stochastic gradient descent. Of course, we are familiar with that. Let's look at like what are the steps that are involved. So let me write it down. Stochastic gradient descent. Of course, batch gradient descent can also be applied with the similar like set of steps. We are going to analyze that also at the end. Now, what we have to do is pick a random data point, xn. So pick xn, that's number 1. Number 2, run forward propagation. What was forward propagation? Well, I begin with the input layer, which my xn equals x0. That's my input layer. And then with certain set of weights, w1, I'm going to get some input for layer 1 transform. And then I get x1, the output from there. And then again, go to S2, the input to layer 2, that again, some transformation, x2. And this process goes on and on. So we are familiar with forward propagation. Eventually, until we get XL, the last layer, layer L. And this is nothing but my hxn, which was my goal. And using this h of x of n, I can compute my error, right? Which is the function compared with my actual value, which is y of n. All right. What is step number 3? Well, my step number 3 is run back propagation. And when I say run back propagation, let me write it down. Run back propagation. That actually means that I have to use these equations that I just came up with. Basically, the idea is to compute all gradients. And to compute all gradients, we need this XL minus 1, that is outputs at each layer, and the sensitivity, that is delta L at each layer, from this equation number 1, right? Because like we really want to compute the gradients. And in forward propagation, the good thing is that we have computed all the outputs. Now we can start calculating these deltas or this sensitivity values at the last layer. And once I can do it at the last layer, then we'll see how it propagates backwards. So what exactly can I do at the last layer? That's my last layer is L. So I can do in my last layer, I can calculate this delta E, delta S, L, right? And let us assume we are working with the squared error and this is a regression problem. And of course, you know that you can translate it to any other type problem, but I'm just focusing on this to make sure that we understand everything. Okay, so let's assume this was my squared error. I'm working with my squared error. And so for any point xn, yn, let me just write it like the point is xn, yn, I can get this sensitivity delta L equals the derivative of this e with respect to, so essentially the derivative of xl minus yn squared with respect to this input, which is s of l. All right, so I get 2 times and okay, xl minus yn, right? And then delta xl stays with respect to delta sl. Right? Yeah, and so this is 2 times xl minus yn, and what is this? This is like the derivative sl, because x is my output, if you remember. And so we've talked about this before, right? So this is like the function that you're using, right? So here the interesting thing is that remember we talked about this theta. We said we are using tan h, right? For all of our activation. And of course, like the same analysis applies to any other function as well. But the derivative for tan h is like really convenient. And so I'm going to substitute that. And because like tan h for s of l is x of l, so that's what I'm going to write here. And let me just, so delta L is 2xl minus yn, and the derivative of s of l, right? And so 1 minus tan h squared SL, which in turn can be written as XL minus YN and 1 minus XL, right? So because the derivative of this is going to be XL, tan h SL equals XL, and there is a square. So I will add that square here as well. Of course, you can go and verify this, but that's it, right? So I got this equation for my delta L, which is the sensitivity for my last layer, right? Now, what I can do using this is that I can compute my delta E with respect to the weights at a layer L. And how can I do that? Well, I can do that because that is nothing but XL minus 1 times delta L, and I just got that delta L from this equation. So what exactly are we doing? Let's like kind of try to illustrate that if we can. And the exact thing that I'm doing is I'm computing this delta L, right? And that delta L for my last layer is helping me get this gradient for that layer, whatever that is, right? And then using that, right, I need, of course, I need delta L minus 1. And so like equation 2, if you look at equation 2 here, This equation can help me get delta L minus 1 because I have this delta L here. So I can compute the delta for the lower layer, right? And then at every step, I'm also getting these gradient of errors as well. So let me illustrate this. As I said, should we move to the next slide? I think that's better, right? So this is layer L, right? It gives me this delta L, which we just saw how. And then using that equation, and if you remember that equation, that was like the gradient computed at SL minus 1, right? SL minus 1, and then the vector multiplication. So that, okay, that component-wise vector multiplication, WL, and then I think it was delta L, right? Now, because we have delta L, we are ready to get the delta L minus 1, right? L minus 1. And in this process, I'm also getting these like the gradient of my errors, which I just got from here, delta W L, which was XL minus 1 times delta L, right? And let me write it down, XL minus 1 times delta L. And the same process goes on. Like in the process, I'm getting delta E, delta W L minus 1, right? And this will in turn help me compute, I would say, delta L minus 2 and also get the error gradients here. And this process like propagates. It goes on and on and on until I arrive at like maybe somewhere here. Let's say I arrive at my delta E delta W1, which would be X0, and then delta whatever was there before, right? This shouldn't be delta. This, yeah, for the layer. Okay, yeah. Let me just like quickly confirm. Yeah, L for L. Okay, so that's fine. And this is for, if this is L and this is 1, right? Transpose. Okay. So we got all the errors, right? And in the process, I got all the sensitivities. And what exactly was happening essentially in every like sort of back iteration, you can call it, in every calculation and at every step, I'm getting that matrix, right? If you again think about them in terms of my layers, so let's say this was my layer L and my delta L, it got me the weights, the WLs, right? Because I have the entire matrix calculated using this. And then what I'm doing is multiply that by my theta calculated as L minus 1. I have this in my, because of my forward propagation, right? And then this gives me delta L minus 1 and so on, right? I keep going until I reach the very first layer. Okay, so in this process, I'm able to compute all the gradients with respect to weights, which is all the weight matrices, right? And essentially what's going on here is that we are running this neural network backwards, except for the transformation step. We are computing the derivative of the activation function, and that's why the choice of this activation function is important. Okay, so what exactly is happening at every, like once we are done with this like calculation of delta E WL, right? Then that's the next question, like what happens? What's the next step? Well, then the next step is my update step that used to be there in my gradient descent. So what was that update step and how will that happen here? So my update step is that update my weights with whatever original weight you have for layer L, of course, minus some eta times delta E, whatever we got from my backward propagation. And then this is like, pick a random point. Let me just like summarize it. What's happening? Pick a random point, run a forward propagation, run a backward propagation, get the gradient, update all the weights, repeat, right? So that's what the stochastic gradient descent is doing. We first ran the forward propagation, we then ran a backward propagation and kept getting the sensitivities and the gradients of the weights, eventually computing the entire matrix of the gradient of the weights. Once we have that, we did the update step, and then we kept repeating until we arrive at some final result, which again depends on a lot of factors like how many iterations I wanted to, or when it converges essentially. So like keep repeating it until it converges. All right, so this was a stochastic gradient descent, and the question comes in like, what is that batch gradient descent here, and why aren't we talking about it? So in batch gradient descent, if you remember from our earlier discussion, for each data point we have to do the same and then save the sum of the gradients and then update them when you have like run over all the data points. So that is kind of like efficient, not efficient, I would say. So we have talked about the pros and cons of both stochastic gradient descent and batch gradient descent, but you can tell that stochastic gradient descent, the one that we talked about, is more popular for efficiency and the parallel architecture that we just saw, right? So now what we have right now is like we have the mechanism to run the neural network, and we understand how we do that. Most likely we have the understanding of the math behind this and why we wanted to do all the calculations that we did earlier, right? So let's look at the application of this neural network with the digits data. Let's look at that. Okay, so here I'm just like summarizing everything, whatever we did. So we actually, well, literally did each of these steps, and you can see a better sort of representation of what we did by hand, but that's okay because now we understand each and every step. All right, and here's the back propagation algorithm in a concise and more, I would say, structured manner, but this is exactly what we're doing. As you can see here, right? So initialization, how the back propagation works, like I began with the last layer and keep going until like keep updating based on the sensitivity and based on like this equation, which is like extremely important because this established the relationship between my sensitivity of one layer with the other. All right, so that's the back propagation algorithm again in a more concise sort of way. Let's look at the digits data that I was talking about. And this is my gradient descent. Okay, so like having said that, having talked about the forward propagation, the backward propagation, and then how the gradient descent works together with that, let's look at the application. I think I have, yeah, here we have. Okay, so top right, you can see this one here is a small neural network with just like two features. And again, we are just using like this bias, but two features were intensity and symmetry. I think we started with that, so we are sticking with that. And then the next hidden layer, just one hidden layer, and you can tell that this is like a very, very simple neural network. The neural networks that are used in practice are way more complex than this. And so we're just like looking at a very small application where you have like 10 perceptrons in the second layer, the red layer, and this is like the digits data, as I said. Now, if we look at the output here, of course, it has utilized all the power that's available to us and a lot of overfitting is happening. But yes, it does achieve this result quite easily, I would say. And although this neural network that you're looking at is pretty shallow, it's not a deep network, but it's demonstrating its power in the sense that like it's going after each and every point and then classifying it correctly. Right. The I mean here, sorry. Here, there is a comparison between the stochastic gradient descent versus batch gradient descent and iterations versus the error. You can see that the gradient descent, like this one, and this is the batch one, and this is the stochastic gradient descent that we looked at. It really converges quickly. The batch one is like slower, and then you can tell why it is slower because it's minimizing the error for one data point at a time, and then it might like mess up the other points. And then in stochastic gradient descent, we are like minimizing the entire in-sample error. So that's why you can see the difference between both of them. And so this kind of summarizes everything that we did in this lecture. This kind of puts together everything. But now you can tell that there is this issue of overfitting with the neural network. And this overfitting is an important issue, as we know now from our foundations. And that is something that we are going to address in the next lecture. When we apply neural networks, this is a very common issue that comes up. And then also, like we have, of course, looked at like these basic ways of computing the error. But in the next video or in the next lecture, I would say we will start talking about like how can we like improvise or improve the error computation techniques. So that's it for this one. Thank you.